Good morning, heroes. Welcome to your first mission briefing. Today, we are going to start our battle preparations to fight our unknown enemy that threatens our very existence. This enemy is so great, it threatens our entire universe. It is your job as members of the RF 6A branch of SHIELD Science and Technology Division to identify this enemy, devise a battle strategy, and defeat this enemy. Today's briefing begins with force in motion. You must learn how to identify the enemy through its strengths and weaknesses. So let's begin. So, first things first, why do you have to learn this? This is a great question. Using the linked Jamboard, I want you to post your thoughts. You only have to make one posting to share why you believe learning this information is important. Be sure to type your name at the end of the post to receive credit for it. If you are watching this video, then you should be using the link to the presentation that is posted in the Google Classroom. It has the date that this presentation was created on Monday, August 31st, or Tuesday, September 1st, with the title Presentation. You will need to open the presentation in order to activate the links. Pause the video to do that now. The study of Newton's laws provides a foundation for understanding motion. You must be able to describe constant or an unchanging motion in order to understand accelerating or changing motion. This also requires you to have the knowledge of the concept of speed, velocity, distance, and displacement. The briefings we will have as you are preparing for your battle are designed to help you gain the conceptual understanding of these ideas. You will be asked to make certain calculations that will not require you to memorize any formulas, but rather to develop an understanding of the concepts to support Newton's laws. As a species, we are innately aware of motion. We are programmed to respond to motion in our environment. We track motion with our eyes and gauge where something will end up based on its motion. Motion is an everyday experience that is completely incorporated into our sense of the way the world works. Motion is one of the fundamental elements of science. Motion holds membership in the grand integrating scientific concept of change. It is important for you to understand this basic idea thoroughly. In the study of physics, the observation of motion is a fundamental process. Understanding interactions in the world often requires precise and accurate measurements of motion. Think about when you're sitting in your room near a window and a shadow catches your eye. You kind of flinch, you kind of duck from it. That is that basic instinct that you have to react to the motion around you. All throughout this mission, you will be looking at motion and measuring the movement of objects using different methods of measurement. You will be looking at graphs and learning to read the graph to determine how an object moves without actually seeing the object in motion. You will be required to complete different battles. That'll be different Padlets, Jamboards, and other activities during each step of the mission. It is your job to complete each battle throughout this mission in order to help save the universe. Once you have completed each battle, you will earn experience points and a code to move into the next level of the fight. Remember, you are a team. It is important for you to work together and save us all from certain annihilation. Good luck, teams. On this slide, you need to click on the shield emblem to access your first mission clue. Be sure to add your name to your post to receive credit. Pause the video now to access the slide in your copy of the presentation. Welcome back. We are going to get started with our mission today by learning about motion. This is going to be the foundation in your battle against the unknown enemy that threatens our universe. Pay close attention, review your mission notes, and work as a team. If you are unsure of who your teammates are, there is a posted listing in the Google Classroom. It is under the heading of Teams and Characters in the Google Classroom. When you open it, there is a tab for the Blue Day classes, which are Monday and Thursday, and the Gold Day classes, which are Tuesday and Friday. Click on your color day and scroll down through the list. It starts with first period, third period, then fourth period. Find your name. Your character is listed out to the side, and then as you go across, you will find an X in the box that indicates the team that you are on. So, what is motion? Well, motion is defined as the action or process of moving or being moved. Well, that sounds simple enough, right? But how do things actually move? Well, that is where Sir Isaac Newton comes in. Newton's laws of motion help us to understand how and why things move. But who is this Isaac Newton? Well, let us review and find out.
Revolutionary English physicist, mathematician, and philosopher Sir Isaac Newton is perhaps the most famous scientist in history. Born to a farmer in 1642, Newton worked his way through school waiting tables and cleaning wealthier students' rooms. He went to university at Cambridge, where he would eventually earn a professorship. During the Great Plague in 1665, Cambridge shut down and Newton returned home. It was during this hiatus that he first conceived the method of infinitesimal calculus, began to theorize the laws of planetary motion, and started his work with light and color. Though his discoveries would change the world of science, he didn't care about the glory and fame that came with them.
He wasn't too concerned with publishing it, making it available to other people, getting glory for his own sake. It was an intellectual challenge that he wanted to deal with.
Every discovery that Newton made had two aspects. First, Newton made the discovery, and second, other people had to discover that he had made the discovery.
In 1671, Newton demonstrated his revolutionary reflecting telescope for the Royal Society, and soon after published his notes on color, describing his research on optics. After a visit from Royal Society member Edmund Halley, encouraging Newton to prove Robert Hooke's hypothesis on planetary motion, Newton wrote his Principia, which introduced his 3 laws of motion and first described the idea of gravity.
Newton's Principia is generally reckoned to be the single most important scientific book ever written, because for the first time it set forth a working, quantitative, exact, mathematical system based upon experiment and critical observation.
His work made him very popular and led Newton to being elected to Parliament. After several years in London, Newton suffered a nervous breakdown. Though he came out of it, his interest in physical science was replaced with philosophy and alchemy, particularly how they both related to a higher power.
Alchemy was concerned with manipulating what were seen to be 4 elemental properties in nature, the 4 elements, earth, air, fire, and water, and realizing that these things made all substances, but you could therefore not only make any other substances, such as gold, but you could also somehow learn the secrets by which God had put the world together.
Newton's later years were spent less in science and more as a public figure. Upon Robert Hooke's death in 1703, Newton became president of the Royal Society, though he didn't get along with many of its members, and made many enemies. Newton spent his final years a wealthy and famous man, whose discoveries made enormous impact on society.
In the century that came after, the 1800s, we find that the fascination with science, with order, and with reasoned knowledge really set the whole tenor of that culture. The one single figure from whom they drew most deeply was, in fact, Isaac Newton.
Now you've learned a little bit about the father of modern science. Sir Isaac Newton died in London on March 31st, 1727. So now let's think about this. A soccer ball sits on the ground motionless unless you kick it. Your binder sits on the table unless you pick it up. If you hold your pencil above the ground and let it go, gravity pulls it to the floor. In all of these cases, the motion of the ball, binder, or pencil was changed by something, but what? What changed it? Okay, so I keep talking about this thing called motion. But what exactly is it that you need to understand? Well, that's just it. You need to understand what motion is. So you see the ball move. You picked up the binder. You see the pencil fall. But how does that describe motion? Now recall, we just defined motion as the action or process of moving or being moved. But what does that mean? Well, motion is observed as a change in position of an object. Notice that the word position is in all capital letters. That means that that is a vocabulary word. Anytime you see words that are in all capital letters or bold print or different color print, those are important. Those are your vocabulary words. So again, motion is observed as a change in the position of an object. We determine position by recognizing a starting point or reference point of the object. The reference point allows us to recognize the change in the object's starting and stopping point. By recognizing the starting and stopping points of the object, we can calculate the distance the object moved. By recognizing the reference point or starting position, we can also determine the direction the object moved in respect to that point. There will be more explanation on these vocabulary words following in the video. So let's take a closer look. Okay, so we have an activity. You're going to be watching a short video clip. Then you will write down any questions that you have based on the information shared in the clip with you. I will give you about 2 minutes to complete the written portion. You will complete this on a shared Google document. After we watch this first 1 minute and 36-second video clip, the next slide has the link to the document that you will need to open and type in any of your questions.
We love drag races here at Motor Trend, and we've become famous for staging quite a few intriguing matchups. But there's one thing we've always wanted to do, and that's to turn our drag racing action all the way up to 11.
That's right, we have 11 of the world's best drivers' cars staged and ready to race.
BMW 1 Series M, Ford Mustang Boss 302 Laguna Seca, Porsche 911 GT3 RS, Chevy Corvette Z06, Ferrari 458 Italia, Nissan GTR, Audi R8 GT, Mercedes-Benz SLS AMG, Lexus LFA, Porsche Cayman R, Lotus Evora S. Just getting this group together requires a lot of people and a lot of planning. Now, of course, this isn't a serious test. So why are we doing it? Because we can. Enjoy the race.
Now, in your copy of the presentation, you should click on the link here and type in any of the questions that may have come to mind by watching that intro to the video. Please do not delete any questions that are already there because they may be repeated questions that you yourself are asking. That's okay. Just keep typing your questions. If the document goes beyond the first page, that's fine. Pause the video now and write in your questions. Okay, we are now going to finish watching the video. I want you to pay particular attention to, at the end of the video, pay attention to the entire video, but pay particular attention to the information that is presented at the end when they start showing you the order in which the cars finished.
So there you have it. Our first 82-cylinder, 5,000 horsepower, $1.5 million drag race. And which car came out on top?
Now, at the end of that video, at the bottom of the still shot of the cars crossing the line, it gave us the distance, the speed, and the time. Those are very important pieces of information that we will need to know. In order to calculate the speed of an object, we have to know the distance and the time that it traveled. So keep that in mind as we proceed. Now, are there any questions from your list that you can answer about the cars now that you have watched the video? One of the questions that should have come to mind was, how far was the race? What was the distance that they had to drive? Well, if you were paying attention at the end of the video, it said that it was a 1/4 mile. Now, that is important for what we're going to discuss next. So let's look at how to measure this motion. Remember that I told you we needed to know the distance. Well, that is what we're going to learn how to calculate. We know that the distance of the race was a 1/4 mile, but how could we have figured that without them telling us? Well, that's where the formula for distance comes in. It is a simple formula. No, you don't have to memorize it because it's fairly simple. And we are going to use this a lot in our class. Now, sometimes you'll be measuring distance. Sometimes you'll have to actually calculate the distance. When we calculate the distance, this is the equation that we use, or the formula that we'll use. Remember that in most cases, the initial position, or xi, will be at x equal to 0, meaning that the amount of change will be equal to xf, or the final position, or where it stopped. And then in that case, d, which is distance, is equal to xf. Now also keep in mind that there will be cases where the initial position, xi, will not be equal to 0. So this initial position will have to be subtracted from the final position to determine the size of the change in position. Okay, now I know this sounds a little confusing, but stay with me. So this is what the formula looks like. D, which is distance, equals xf, the stopping point, minus xi, or the starting point. So we will have to use something to measure it. In most cases, we'll be able to use a ruler or a meter stick. Sometimes in the instances like our race, we actually would have had to use the car itself. So we're going to practice more about those calculations in just a few minutes. But now I want to look at graphing motion. Remember, I told you that we could look at a graph and see how an object moved without ever seeing the object. So let's look at this. Now, graphs of motion are very easily interpreted. You just have to look at the labels on the axes and the shape of the line. So what does that mean? Well, these are types of motion graphs. It's distance, which we would have calculated over time. How long did it take? How far did it go? And how long did it take it? So on a motion graph, when there is a straight line, it always means that something is constant. A constant is something that is unchanging. Okay, so look at this one over here on the left. So we have distance on the y-axis and time on the x-axis. Now look at this line. This line goes straight up, right? Well, on a diagonal, but the line is straight. It continues, okay? There's no change in the slope of the line, how much it rises, okay? This means that this object has a constant speed. it's staying the same. It's not changing. It's not speeding up. It's not slowing down. It stays the same. Okay, so the line is straight. So constant speed means unchanging speed. Now over here on the right, we still have distance over time, but notice our line. Our line goes straight across. It's flat. Well, this flat line represents no motion. The distance isn't changing, but the time is going by. So this object is actually sitting still. This could represent your soccer ball, your binder sitting on the table, or you holding your pencil above the ground before you let it go. Okay, so a diagonal straight line means a constant speed. A flat straight line means no motion. It's sitting still. Okay, now look at these. These graphs have a change in them, don't they? They're curved. Well, on a motion graph, a curved line always means that something is changing. Okay, so we still have distance and time, but notice our object. It starts off and then all of a sudden it starts to go up. Well, that means that the speed is changing. This one is accelerating. This would represent our cars on the racetrack. They were sitting here at 0, and then they started to take off, and then the further down the track they went, as time went on, they kept getting faster and faster. So the line starts to curve. Now over here, we still have distance and time. Notice that this line is curved in the other direction. Well, this means that they're starting to slow down. Okay, so over here, they're at top speed. Over here, they're starting to slow down. This would be the cars coming to the end of the race. Okay, so now they're starting to slow down. So the point in showing you that video was to show you the motion. They're sitting still at the starting line. Then the man says go, and they take off, and they start to speed up, and then they're at top speed. As they approach the end of the race, that XF spot, they're over here, and then they start to slow down. Okay? So now, there is going to be a separate demonstration that I will add to this video for you to take a closer look. We're also going to be completing the exit slip that is in the Google Classroom that goes along with this video. You'll need to open it to be able to complete it following the demonstration. Now, do not work on the form until the demonstration is completed. This is your exit slip for today. And the code that you'll need is right here, because there is a code on the exit slip for you to be able to complete it. So hang tight. The demonstration is on its way. Okay, as you can see in this video, our starting point for the air trolley is at 0 if we use the reference point of the back of the straw. Okay. If we use the front of the air trolley, then our propeller is at about 15 centimeters. So depending upon the reference point, the point on the object that we choose to measure from, we can start at 0 or we can start at 15 centimeters. So what we have to do is we have to wind up our air trolley. Okay, and then when we let the propeller go, the motion of the air trolley is going to take it down this wire, and then we can measure how far it went. So I've tightened it up, and here we go. And it didn't move. Okay, so let's try it again. This is the problem with experiments. Okay, here we go. Okay, it barely moved, but we can measure that. So if I put the ruler back up here, we were at 0. So if I move it to the end from 0 to where it was, so 0 to where it is, it traveled 4 centimeters. So our reference point from the back of the straw was 0 against the door to 4 centimeters. The back of the straw. Well, about 4.5, almost 5 actually. Okay, so let's try it again. This time we're going to tighten it up a whole bunch. So we're going to start back here at 0. We're going to give it a good twirling. Okay, so we're at 0 against the door, and here we go. Ooh, we got a little distance that time. Let's see. So it went 0 to 30. So 30 centimeters. And then go from there, and we add on about, let's see, it's about 20 more, so it went about 50 centimeters. Okay, so remember, when you're choosing a reference point for your object to measure the distance that it traveled, you have to pick a reference point. For this demonstration, the reference point is easiest to start at the back of the air trolley. That can be point 0. And then that way, no matter where it moves to, we always measure to the back, okay? It's a little harder when you want to measure to the front of the air trolley out here by the propeller, because it's harder to make accurate, okay? It doesn't, as long as you are using the same reference point. So if 0 is my starting point at the back of it, as it moves, I don't want to go from an initial measuring at the back to my final measuring at the front. That throws off the measurements. You always have to use the same reference point. So if I start at the back, it has to end in the back. If I start at the front, then it ends with the front, okay? All right, so let's practice doing our calculations in the exit slip. Remember that distance equals XF, which is the final point where it stopped, minus XI, the initial or the starting point. Okay, so from the video, we had some initial vocabulary. So this is your vocabulary words. Position, meaning where something is. Reference point, the starting point you use to describe the motion or position of an object. Distance, how far an object travels. Direction, it describes the movement towards or away from the reference point. And motion, the process of changing position. Now, we also talked about how to measure distance. So as you can see here, I have created a chart to help explain. So remember that measuring distance is the change in position. So D equals XF minus XI, where distance, D is distance, XF is the final position, XI is the initial position. Now let's look at our starting point. So as you can see on the car, we have two different marks, and I've got XI on here twice. So this is my initial reference point. So I can either use the back of the car or the front of the car. You can use any position on the car you want, but the back or the front are easier to measure from. So as you can see here, XI here would be defined as 0. And XI, if I use the front of the car, is defined as 13.5 centimeters. Now, I can show you how I did that. So I have my ruler, and I put 0 at my initial spot. Then as you can see here, the front of the car, that's a 13 under there, at 13.5. Okay, so I recorded what my distances were, or my initial positions were. And then the car travels, and then it stops. So then I have to measure to my final two positions. If I start over here measuring at the back, then I want to measure to the back where it stopped. Same thing if I use the front. I want to use the front of the car where it stops. So how do I measure that? Well, I come over here and I have my 0. And then you can see that I marked it. It's at 30. So then I'm going to move up the ruler. And then I mark it again. It's at 15.5. So 30 plus 15 is 45.5. So that's where I get my final position. Now to calculate the distance traveled, I plug in my information. So XF was 45.5. So I plug that in here, minus the XI, which was 0. 45.5 minus 0 is 45.5. And I used the centimeter side of the ruler, so it's in centimeters. Now, the same thing for if I use the starting point of the front of the car. So I put my 0 down, and remember it started at 13.5. That's what I recorded. So then I measure. Again, it's at 30, and I scoot it up, and it's at 29.5. So 30 plus 29.5 is 59.5. And I do the same thing. I just plug in my information. So 59.5 minus the 13.5 from the initial gives me 45.5 centimeters. As you can see, it doesn't matter which reference point I use because the distance is going to work out the same. But you have to make sure that you use the same reference point for the starting and the final position. You don't want to switch them up because that'll mess up your calculation. Okay, good luck, guys.